Here is another visualization of a coherent network architecture. In this figure, you can see that we have a small coherent network in which we have only 4 by 4 nodes. So our output map or the grid is basically consists of total 16 neurons, and all the 16 neurons are basically arranged in a 4 by 4 grid map, and these are connected to the input layer. The input layer is being shown here with this green color, and you can see that the neurons, there are two neurons in the input layer, and the two neurons are basically fully connected to each neuron present in the output grid map. So each node has a specific topological position and xy coordinate in the lattice or in the grid. So each neuron has an x value and a y value, which is their xy coordinates, and each neuron contains a vector of weights, right? So we have a vector of weights. So there is not a single value, a single weight value, but a vector of weight vectors. And it contains a vector of weights of the same dimension as the input vectors. If the training data consists of vectors v of n dimensions, so if we say that our training data has n dimensional vectors, so we can represent them with v1, v2, v3 up to vn. Then we can say that each node will contain a corresponding weight vector w with n dimensions, right? Because we have n dimensional input training data set vectors, so their corresponding weight vectors will be n dimensional with w1, w2, w3 up to wn. So we can see that each of our data vectors have a corresponding weight vector assigned with them, and this is very much similar to our a standard neural network architecture. So just to have a motivation for SOM, let's have a look at another example. So here is a world poverty map, and you can see that a SOM has been used to classify statistical data describing various quality of life factors such as state of health, nutrition, education services, etc. And you can imagine that if we had to do this manually, then it could be a very hectic and time consuming task. But with the help of SOM algorithm, we basically created these clusters or classes, and depending upon the health, nutrition and education services of different countries. Countries with similar quality of life factors end up clustered together, right? So all the countries which have similar characteristics related to health, nutrition and other services, they are basically formed in clusters which are very similar or closer to each other. And the countries with better quality of life are situated towards the upper left, which is this corner. So we can say all these countries have a better living, and the most poverty stricken countries are towards the lower right. So these are the countries which are basically towards the most poverty levels. So you have seen that with the help of SOM, we have basically sorted out this very complex problem very easily. So now let's have a detailed look at the SOM algorithm, and let's see what are the main steps that are involved in order to make clusters through SOM. And you will see that most of these steps are already known to you, and we have already used most of these steps in different algorithms. So initially we basically try to initialize our weights, and we set a max value of r, and we set a learning rate alpha, right? So these are our initial parameters. We need to initialize our weight vectors, we need to set the value of r, and we also need to set the value of alpha, which is our learning rate. So we execute all these steps from 2 to 8 in a loop, and we have a stopping conditions like we have in different stopping condition in different algorithms. So we also have a stopping condition and based on this stopping condition we basically terminate this loop here, and within this loop we basically execute these steps from 2 to 8. And the step number 2 is basically we have for each input vector x, because we have different input vectors and we need to do some processing on each input vector. So for all the input vectors, one by one we will basically be repeating all the steps from 3 till 8, right? And in step number 3 we will compute the Euclidean distance for each neuron j. And in order to compute the Euclidean distance we have the same formula which we have used previously so many times. So we are computing the Euclidean distance for each neuron j. Find the index j such that d of j is a minimum. So once we have all these distances, so d of j is basically representing the distance here. So once we have the distances here, we basically need to figure out the index j for which the value of d is minimum, right? So we are looking for the minimum distance value for j. For all neurons j within a specified neighborhood of j and for all I, then what we need to do once we have the minimum distance, we basically need to update the weights for the neighborhood. So we have already a neighborhood for which we have decided the value of r, and this is the equation through which we will update our weight matrix. And you can see that this equation is very much similar to our equation which we have already used in neural networks to update the values of weights. So we have a new weight value here which is being computed with the help of older weight value, right? And with the multiplication of the learning rate, right? So you can see this is the same equation which we have already used, and by using this equation we can calculate our new weight matrix. Then once we have updated the weights, we need to update the learning rate. So we will have an equation through which we will basically updating the learning rate. And the importance of learning rate is that it is a decreasing function of the number of epochs, right? So as the number of epochs increases, the value of alpha or the value of learning rate will be decreasing. Reduce radius of topological neighborhood at specified times. So in parallel, by performing all these operations, we will also be reducing our radius, which is the topological neighborhood. Then once we have all these steps in our loop, then we will test our stopping condition so that we can see that whether we need to stop the algorithm or still we need to go further. And the stopping condition is typically a small value of the learning rate with which the weight updates are insignificant. Now let's have a example so that you can have a good understanding of all these steps which we have seen in the basic SOM algorithm. So we have a simple example here in which there are only 2 neurons in the output layer, right? So in order to keep the example simple, we have 2 neurons in the output layer, right? So you can say that this is our output layer or our grid map, and we have 4 input neurons x1, x2, x3 up till x4 in the input layer, and all the neurons present in the input layer are connected to each neuron in the output layer, and all the connections have their corresponding weight vectors, right? So this one has w11, this one is w21, this one is w31, and this one is w41, right? So if we arrange these weight matrices in a matrix, then we can say that our initial weight matrix will be w11, w21 for one input output neuron, and another weight matrix for the second output neuron. And we have some initial values corresponding to each weight vector.